Okay, so today's Saturday session has to do with experiments that you're supposed to be familiar with because in paper three, the first like 10 marks of your paper three are a lab-based question. So there's about 4 or 5 labs that we're going to go over in the next couple Saturday sessions that discuss certain labs that you need to be familiar with and to the extent at which they're going to ask. It's going to be less about actually doing calculations and more about knowing the procedure and the sources of error and why you do certain things in those experiments. And so you'll see what I mean when we kind of go over this first one. We'll see if we can get through 2 today, but we'll definitely get through at least this first one here. So the first experiment we will do is an empirical formula lab. Now, this is actually be split up into 2 different types of empirical formula labs. Okay. Now, the purpose obviously is to determine the empirical formula or the hydrate formula. Okay, there are compounds that are hydrates where water is attached to them that also have a formula that you may need to know. And we're going to kind of divide this in half for y'all to kind of understand that. Okay, so I'm going to kind of split it down, maybe not perfectly halfway, but maybe like this. Okay, and so there's a variety of different experiments that you can do to accomplish empirical formula. Okay, you can do a combustion problem where you're combining like a metal with oxygen to figure out the empirical formula of the compound. Now, notice I'm not predicting the formula of the compound, so I'm not going to balance anything like that. I'm just understanding that magnesium is going to bond with oxygen. The purpose of the lab is to find out what those subscripts are. So you're not assuming because you know Mg is 2 plus and O is 2 minus that it's going to be MgO. You are doing an experiment to see if your experiment gets you the same ratio as expected. Okay, so usually with combustion, you're going to use a crucible and a Bunsen burner because the heat will allow the oxygen from the air to react with the magnesium. And just an FYI, if you remember the magnesium, it gives off light. It gives off a bright light when it combusts. That's kind of an aside that you may need to remember. Okay. Another technique is, for example, you could react an acid with a metal. So maybe you have something like this to form this. So some unknown compound and hydrogen gas as well. When you're doing this, though, you're going to be using an evaporating dish to boil off the water because these experiments are usually aqueous, and so you're going to have water. The H2 will escape, so all you'll have left in the dish is aqueous. Let me zoom in a little bit there. Aqueous magnesium chloride. So then the only thing you need to separate now is the water from it. So you boil off the water so that you're left with just the magnesium chloride salt. And the last thing is decomposition. You might start with a metal oxide and decompose it into its different elements. So generally this just requires very high heat. So there's different ways to do this experiment, but in the end, all you're looking for is a change in mass. because that change in mass either means you lost an element or you gained an element in the compound, which will allow you to calculate empirical formula later. And when we talk about that in the calculations, that's where that will come into play. Okay. Questions about these three different types of experiments? Again, they all accomplish the same thing, just in different manners. Yes, Sol. Correct. Because in all these reactions, you're either going to gain mass from a new element or you're going to lose mass from an element you lost, which will then allow you to figure out the ratio of the elements, because the mass that you have left over will be the mass of one of the elements, and the mass you either gained or lost will be the mass of the other element. So then you can do empirical formula. Does that make sense? Okay. All right. We got this. Let me switch to the other side now. Okay. A hydrate is a compound that has water attached to it, and written something like this. Okay. So the formula, there is a dot. The dot stands for hydrate. So what this is saying is there's a certain number of water molecules that are attached to this copper sulfate. And what we're doing is we're trying to heat it up so that we separate the water from that compound. So essentially you're vaporizing the water so that you're left with just pure compound. And generally you do it in a crucible with heat. So you're just trying to get to the point where the water boils off, but the copper sulfate doesn't. The other compound doesn't. There is usually a big difference between the boiling points. So as long as you're using a Bunsen burner or even a hot plate, you should be able to boil the water off without any boiling off any other compound.
So what's the difference between the acid with metal and then the hydrate form?
That's a good question. The hydrate formula is not an actual reaction. It's just a sample of a compound that you're just trying to eliminate the water from. In the acid with the metal, the acid is in water. It's mixed with water. So there's just water that the environment's in, and you're trying to get rid of that so you can get the mass of what the salt that's left over.
So the hydrate formula is like the real reaction occurring, and then the acid with metal is just like a
The water
theoretical
is
or
no, well, no. The acid with metal, the acid has water because the acid is dissolved in water. So when you
oh
do the
okay oh
reaction, you're gonna just have water left over. You got to get rid of that.
okay
In the hydrate formula, the compound comes attached with water initially, and then your job there is to
okay
boil the water off to figure out how much actual compound you have.
I see. Okay, thank you.
You're welcome. Okay. Now, for data collection here, essentially it's what data do we need for this experiment to work? Okay. So generally speaking, what we do is we have three pieces of data. Okay. We have the mass of the container and sample before any reaction. Generally, we do this with a container because oftentimes when you're heating it, you're not going to be able to separate the compound from the container later on. So we want the mass of the container and the compound because we may not be able to separate the two species from each other later on if we heat it too much. So the mass of the container, empty, and then the mass of the container and sample after. So what does this accomplish? Well, these two values get you the mass of the sample before. And these two values, the difference between these is substance mass gained or lost. Okay, so you're using these values and finding the difference in them to figure out information that you need to have. Yes, the first, second one, yes. And then once you have those two values, then you can know the new or lost species is the difference between those, right? So like if we have the mass of the substance that's gained or lost, we know how much we had before and we know how much was after. So that gain or loss must have been the new element or species that's introduced or removed. So like, for example, in here, that would be looking at, the blue would be looking at the amount of oxygen that's lost here, or the amount of chlorine that's gained here, or the amount of oxygen gained here, or the amount of H2O lost here. So that new mass means you either gained oxygen or gained chlorine, or you lost oxygen or you lost water. But that's what that value represents. In the mass before, I guess I would say, since we're doing this, the mass before would be of the mg. The mass before would be the mg. The mass before would be all of this. The mass before would be all of this. Does that make sense? Questions about that? Because that's the data that we're going to need for this reaction. Okay. Now, one thing about this process that I want to kind of stress is that you heat the container until mass is constant for 3 measurements. So if you're heating these crucibles or evaporating dishes and stuff like that, you keep heating it until the mass is constant for 3 measurements. Okay. Why do you think that's important? What's the purpose of heating it until the measurement's constant 3 times? What's the benefit? What's the purpose of that? Sol? Yeah, you make sure everything's completely reacted, right? So if your mass is still going up, that means, or mass is still going down, that means something's still happening. But if your mass stays constant, then you can assume the reaction is complete. Because the other compound won't evaporate or anything like that. Yes, Christoph. Of this specifically, or yeah, we're gonna do another lab because this is going pretty quickly, actually. Yeah. Okay. We do make some assumptions here. Okay. So a couple of things that uh, we're assuming here are the container mass is constant, meaning that for some reason the container isn't gaining or losing mass because it's reacting with the heat or anything like that. Two, we're assuming there's no contamination. So these are all pure substances, whether they're compounds or elements, they're all pure. We're assuming that nothing else reacted in this. Actually, ignore that line. We're also assuming over here on the right that all mass lost is only water. And over here, we're assuming that reactions go to completion. So this is the kind of stuff that they'll ask you in this paper 3. They'll say, given the following data, they might say like, here are the values of the mass, and the mass is still going up, and they're saying they might say, state and explain why this data can be used. And if the mass is still going up, that means you can't be used yet because you're not done with the reaction. But if the mass has stayed constant for 2 or 3 trials or 2 or 3 measurements, then you say, well, the reaction is complete. It's kind of stuff like this. They're not going to actually have you do calculations and stuff like that. They're just going to have you explain the techniques and the processes of this. I am going to go over the calculations here, but it's not super important for this. Okay. Oh, yeah. Okay. Okay. Now, analysis. I'm going to split this up into 2 as well because the calculations are pretty much the same, but I'm going to label them a little bit differently. So that's what I'm going to say here. So essentially, what we're trying to accomplish here is to get the mass of the metal and the mass of the other ion. Like that's what you're accomplishing with this because you know the mass of the metal through your calculations and you can know the mass of the ion. So for example, up to the first 2, we know the mass of magnesium already because we massed it before. And then we can figure out how much oxygen is added because how much mass it gained was all oxygen. And the last one, we know how much was silver oxide. So when we heat it, whatever's left is just silver, and whatever was lost was the oxygen. So in all these techniques, we should have these 2 values at the end, the mass of the metal and the mass of the other ion, whether it's oxygen or chlorine or whatever, or chloride, I should say. And we're going to divide it by the molar mass of each species to get the moles of the metal and the moles of the ion. Let me zoom in a little bit there. And once we get the moles of the metal and the moles of the ion, how do we find the empirical formula from that? What do we have to do? Once we have the moles of each, what do we do? Divided by the smallest one. And that should get us X and Y for our subscripts. Remember, if your ratio is like 1.5 to 1, you multiply anything that's 0.5, you multiply all of them by 2. So the ratio becomes 2 to 3. If it's 1 to 1.66 or 1 to 1.33, it can be any 0.66 or any 0.33. I'm just making an example here. You multiply by 3 to get rid of that decimal. So this would be, 3 to 5, and this would be 3 to 4. Okay. And remember, don't round to the very end because these numbers, these problems are kind of set up so that you get very, very nice decimals. So if you're doing a problem, you get like 0.75 or 0.8, that's not 0.66. You did something wrong. So like they will have it set up so it's really, really close to 0.5. Maybe it's 0.48. Maybe it's 0.52. That's close enough. Yes, that. You shouldn't. Like, I guess theoretically you multiply by 4 because that's really close to 0.25, but I haven't really seen a problem that was, yeah, I think in those, in the multiple choice, you're best off actually trying to hack the system and calculate the answers and working backwards from there. Like, I would do that because you don't have a calculator. So you might be able to estimate a little bit better and round like that. Okay. Questions on this? Okay. Now, for the hydrate, it's the same process, but in this case, you have copper sulfate and the mass lost is of water. So you are still dividing by the molar mass of each substance. It's just that it's not elements anymore, it's actual compounds. So you get the moles of CuSO4 and the moles of H2O. And I'm going to tell you right now, for hydrates, you should be dividing by the moles of CuSO4 because water is always going to be a multiple of more than one or more. So it should always be CuSO4. And then you'll get 1 and then some value here. And that value becomes the value that you put in front of the formula for the hydrate. Questions on that? Yes, Saul. Yes. Yeah. So to kind of repeat Saul's question, when you write this out, if x is 3, you would write that. That's the way the formula would look. You still keep the dot there. Okay. Questions on that? Okay. Bless you. So with this, we do want to acknowledge different errors and things like that in this case. And so random errors, I can't think of as many errors for this that might be random errors, because random errors are ones that fluctuate either way and they're kind of hard to kind of control. But I would say systematic errors, there are several kind of systematic errors that you might have to deal with. Okay. And it's important that you know the error and then also how it affects the data. And so, for example, let's say you noticed that the metal or the magnesium is oxidized before. Okay. So if the magnesium is oxidized before, how does that affect your data? Is the mass going to be all pure magnesium? No. So if your mass is 1 gram of magnesium, but it's oxidized, how much magnesium do you actually have? Less than that. So in other words, you end up having less magnesium to react than you thought you did. And if you have less magnesium to react, then guess what? You'll have less chlorine to react as well. Yeah, that's good. Yeah, like just yeah. So if your amount of Cl is less to react, then your ratio is going to be too low. Because remember, you don't know how much magnesium you reacted, you just have the one you measured. And then if you have less Cl to react, then the ratio is going to be too low. So let me make sure I'm saying that right. Because the Mg to Cl ratio, yeah, will be too. Am I saying that right? Because like if it's supposed to be 1 to 2, it might end up being like 1 to 1.5. Would y'all say that's too low? Yeah. So what happens is if you have less magnesium, less chlorine reacts, but that's how much you're measuring. So in reality, you're actually reacting less magnesium with the right amount of chlorine, but you don't know that because you assumed all your stuff was magnesium. So therefore your chlorine amount will be too low, so then your ratio will be off. Does that make sense? Okay. Yes, correct. So you know MgCl2 should be 1 to 2. But if your ratio is 1 to 1.5 or like 2 to 3, then that's one of the possible cases, one of the possible reasons for why it's too low. Okay. How might you be able to fix this error? What's a way that you could prevent this error from happening? Yes, Christoph. Oh, I see what you're saying. Store the magnesium in a vacuum. But let's pretend I gave you the magnesium and you already noticed it was oxidized. What could you do to remove that oxidation? Scrub it with steel wool. You just know that from your IA, right? Yeah. So if you scrub with steel wool, it will remove the oxidation. So therefore, it'll work. Okay. Oh, gotcha. So it will remove the oxidation. So they might ask you, how's one way that you could reduce this error? So you'd say, well, I'd scrub the metal with steel wool to remove the oxidation so that my mass is more accurate. This is the kind of stuff that you have to think about in paper 3. They don't talk about this as much in paper 2 and paper 1. This is more of a paper 3 kind of laboratory concept. Option correct. So the first 20 marks, the first part is one lab question and one database question that you can't prepare for. Like it's just to pretty much interpret this data, come to conclusions, stuff like that. But there's no way you can prepare for that other than looking at previous questions. But they'll just pick random data that you've never seen before. Like one year they were doing like greenhouse gases and like temperature effects and stuff like that. So you can't prepare for that specifically. You just have to interpret the data they're giving you and then come to conclusions and stuff like that. So it's like critical thinking. Okay. So another one. Okay. Okay. Not all water is lost. So, like, let's say, for the example of hydrate, let's pretend we were heating and you didn't get to 3 measurements of the same. Okay. How would that affect your value in the hydrate here? So, if you didn't get rid of all the water, then the mass that you have left over is going to be what? If you didn't get rid of all the water, the mass that you get at the end will be what? Huh? Greater. Too high. So, your final will be too high, which means your mass of water is too low. Because if you didn't get rid of all the water, then the mass that you thought was just pure solid has some water attached to it. So therefore, it'll be too high. And then the mass of the water is too low. And then your X value is too low. And these are systematic errors because these errors always affect it in the same direction. So systematic errors always affect it in the same direction in your experiment. Questions about that? Okay, so change my mind. We're doing calorimetry because I didn't want to do both like kind of hard experiments on the same day. So we'll do kind of one easy, one hard for each one. So calorimetry here. Okay, calorimetry is from the topic 5, enthalpy, and the purpose of this is to solve for delta H. Okay, of reaction. So the molar enthalpy of the reaction, not just Q, because yes, we do solve for Q, but usually this experiment takes it all the way to delta H. RXN is just an abbreviation for reaction. Okay. And there are 2 types of calorimetry that you might have to deal with. And so I'm going to talk about both of them. So we are going to kind of split this up, at least in the procedure part, we're going to split it up in half. Actually, we'll do it like this for now. Okay. One type is what we call coffee cup calorimetry. Okay. Generally, coffee cup calorimetry is called that because it's done in styrofoam coffee cups. Okay. So usually you're mixing solutions together in styrofoam cups. Okay. Because they are insulators. So they're the cheapest and probably effective enough for the experiment that the styrofoam insulates and doesn't absorb heat very well. So you'll have essentially two cups kind of laid on top of each other, and then you'll have the thermometer to measure the change in temperature of the solution. Okay. Now, you can use coffee cup calorimetry for a variety of different experiments. You can use it for neutralization, where you're combining an acid and a base together to release energy. So, like for example, sodium hydroxide and hydrochloric acid to form salt and water. The temperature of the reaction should increase. You could also do it for like a metal and acid. So like you could do Mg plus HCl yields MgCl2 plus H2 gas. And you can even just do it for the enthalpy of solution, where you're taking a solid substance and you're making it into aqueous by dissolving it in water. And some of those are exothermic, so you can measure that as well. So for example, if I put sodium hydroxide solid into water, it will give off heat as it's dissolving. So we can measure the amount of energy that is. The term enthalpy of solution is a higher level concept, but I wouldn't be surprised if they use the same concept in SL, even though you don't know what enthalpy of solution is. It's still just a reaction. Okay. Questions on that? Because it's dissolving in water. So you're not melting it, you're just putting a solid amount of water to dissolve it. All right. The other type of reaction is what I'll call combustion calorimetry. That's not a technical term, but usually this is when it's used for. Okay. And essentially, you use an alcohol burner and a beaker of water. Okay. And what you end up doing is you have this burner and this wick And you have this beaker of water. A little bit. I mean, I guess I've been doing this for like 13 years now, so I guess I've been drawing beakers and alcohol burners for 13 years now. No, it's not your fault, Soul. Not everyone is as gifted as me. You hear that, YouTube? Okay. So the idea is that the fuel is in here and it burns and it loses mass. Oh, that's really hard to read. It loses mass as it's burning, and the heat is heating the water and the beaker as well. In some experiments, they might give you the calorimetry constant of the beaker so you can get a more accurate heat amount, but other times they might not. So it depends on the experiment. But you're essentially measuring how much heat the combustion reaction is releasing to the water above the alcohol burner. I don't know if I want to put this in error or if I want to put this right here. I'll put this here because we have a little space here. As a note, for both experiments, we'll just draw this here. As a note for both experiments, I would suggest that you always stir, okay? In most of these experiments, they have you stir, okay? What could be the reasons for why you should stir these reactions? What's the benefit of stirring? Yes, Oliver. Right, so increase the reaction rate, right? So it speeds up the reaction so that the heat loss is going to be less. Nick, yeah, you're distributing the heat better as well, more equally. So both of these things help you minimize the error in your experiment. So generally speaking, you should be stirring. And maybe that would be a question like they said, state one way you could reduce the amount of heat loss to the surroundings. And you might say, well, stirring the reaction would be able to accomplish that. Okay. Well, remember, the beaker is what's transferring the heat to the water. So so because it's directly heating the beaker, which is heating the water. So it's a little bit trickier to do that. Sometimes they'll do what's like a bomb calorimeter where they put like a sample of like the fuel in a bomb calorimeter and like combust it and then just measure the heat, the air like heats up. But I haven't seen that experiment in the IB. That's much more accurate, huh? Because it's an explosion. So like it's an explosion and you measure how much heat the temperature increases the air and that you there's a specific heat capacity of air as well, which allows you to calculate how much is heating. Okay. I mean, yeah. Okay. All right. Data. Okay. Assumptions. Okay. There are certain things that we assume that allow us to conduct this experiment. Okay. One, the volume of solution is equal to the volume of the water. We're assuming any chemicals in the water have a um, negligible amount of effect on the volume of the water. Okay. 2, volumes are additive. We make that assumption. So like if we're mixing 50 milliliters or 50 centimeters cubed of acid with 50 centimeters cubed of base, we're going to assume that the total volume is 100. Even though it's not technically correct, that's our assumption to make our lives a little bit easier. Yeah. So like let's say you're doing a coffee cup calorimetry where you're measuring, like you're mixing 50 centimeters cubed of acid with 50 centimeters cubed of base. We're assuming the total volume now 100. Even though technically, for one reason or other, it may not equal exactly 100 when you mix them together. Because sometimes when things react, the density of the solution actually like increases or decreases. Like in volumetric flasks, it's really important because like if you measure a liter or a decimeter cubed of water and you mix a certain amount of solid in it, sometimes the solid mixing it actually decreases the total volume by attracting the water more closely than it normally would. So yeah, like that's why you like mix it with half the amount of water and you fill the water up until the level that you require after that. Don't fill up to the level required and then add it because you'll notice that the volume will actually decrease. Small amounts, but it will decrease. Okay. 3, the mass of the water is equal to the volume of water because 1 gram of water is equal to 1 centimeter cubed of water. And 4, the heat of the water is equal to the opposite of the heat of the reaction. So whatever the water absorbed and water released is the opposite of what the reaction did. Okay. Okay. Data that you need. Okay. 1, mass of water. Total at the end or of the beaker that you're using to heat up. 2, specific heat capacity of water. Is that given to you? Yes, but you still need that value. C, you need the change in temperature, which is TF minus TI. Now remember, in some of these reactions, you'll get a graph that looks like this when you're collecting data. Okay. And what you need to remember is that, yes, this is your initial, but your final is generally drawn like this. Generally speaking, we figure out the final temperature by taking the cooling part of the line and extrapolating it back to as if the reaction happened instantaneously. So that might be something they do on this. They might say, determine the final temperature of the experiment. And you'd have to work backwards with the graph to figure out what it would have been if it was instantaneously. So the correct final temperature is that point, the point I highlighted there, not the peak of the curve. So that's something that might show up on paper 2 or paper 3, to be honest with you. That's a graph of the temperature change of the reaction. So like pretend we had a Vernier Lager Pro temperature probe in the coffee cup or like in the beaker above the alcohol burner, and we are just measuring temperature over time. And the reaction starts here, obviously. This is T equals 0 because you let it stabilize and then you do the reaction. So T equals 0 is not the origin. It's when the reaction starts. Because a reaction doesn't happen instantaneously. So what you have to remember is as the reaction is happening, there's cooling that's happening at the same time. So like, because if it takes 20 seconds to actually completely react, over that 20 seconds, even though you're putting heat into the water's also cooling at the same time. So what we do here is we remove the cooling factor of the water by drawing a a tangent line to this curved part, and that eliminates all the cooling that is happening and eliminates the time it takes for the reaction to occur and makes it spontaneous, like instantaneous. So it minimizes your error. That's essentially what it does. Correct. Exactly. You're converting the graph so that it was instantaneous. Okay. Questions? Okay. Other data you need to know. Okay. For the coffee cup, you should know the molarity and volume of solutions and the mass of any solid if it's there. So if there's a solid in the reaction, you need to know the mass of that. In combustion, you need to know the initial and final mass of the burner because that will equal the amount of fuel burned. So when we measure the mass of the burner before and after, then we are able to figure out how much actually combusted. And that will help us for our delta H later on. Questions?
Mr. Chuang,
Yeah, Jamil,
can you move over to the left? Yeah, thank you.
no problem. Huh? Oh, yeah. So when we figure out how much heat the water absorbed or released, that has to be the opposite of what the reaction did. So, like, if the temperature of the water went up and it gained heat, you're assuming all that heat came from the reaction only. Does that make sense, Oliver? Okay. Analysis. Now, the analysis is not going to change for either reaction. The idea is you need to know the temperature change, and you're dealing with water here. If it's coffee cup, you're probably adding the volumes of the water together. If it's combustion, you're just having the starting amount of water here. But the Q of the water equals the mass of the water times the specific heat of water times the change in temperature of water. And again, I'm reinforcing the fact that when you do this, everything's of the water. All the measurements you have are of the water. The volume of the water becomes the mass. The specific heat is constant. The change in temperature you measure is also the temperature change of the water. And that value you get is then the opposite sign of the value of energy the reaction gave off. So if water absorbed 1400 joules, that means the reaction released 1400 joules, negative 1400 joules. And once you get that, oh yes, Christoph, specific heat capacity. So 4.18 joules per mole grams. Sorry, not joules per mole, excuse me. I was thinking about something else. Joules per gram degrees Celsius. Yes. Yeah, sure. Oh, and no, no, you need, sorry, it's not plus. I should rewrite that. If you know if you know these, the and the values, the difference between them is the mass of the fuel burned. Sorry. So you should measure the mass of the burner before, measure the mass of the burner after, and find the difference between that, and that's the fuel amount of fuel. Yeah. Yeah, final minus initial. Sorry, initial minus final. Yeah, initial minus final. So these values on the right, the purpose of them is for this part, because delta H is equal to Q of the reaction over the moles of the limiting reactant. Okay. So whatever moles of reactant is the limiting, you're going to divide by that value. Usually in coffee cup, they make it so the moles are the same for each so that you don't have a limiting reactant, but double check to make sure. Limiting reactant. Mm-mm. The surroundings is the water. Right. So it should be the opposite. Yeah. You can never measure the temperature of a reaction. Temperature is always part of the surroundings. So anytime they say temperature or something, that's usually of the water if you're measuring it. Limiting reactant. So if you're doing a chemical reaction, you need to make sure that your limiting reactant, because your limiting reactant is going to affect how much you can produce energy wise, right? Because once that runs out, you can't produce any more energy. So be careful about that. I've seen times where they'll say like, um, for example, they'll say like in this problem, they'll have like 50 milliliters of HCl and 50 milliliters of NaOH, and they'll say, how would the value change if we did 55 milliliters of NaOH and 50 milliliters of HCl? It wouldn't change because you have the same limiting reactant, so you should still get the same value for everything. Okay. Questions? So this one's a little bit less math heavy of an experiment, but there's a lot of issues that we have to talk about here. Okay. Obviously, with this one, because we're not using digital values, we're using graduated cylinders and stuff like that. That's where your measurement, your random error comes into play. So when you're using a graduated cylinder or you're using like a thermometer, this is where like your random error can come into play because you're having to estimate digits. And the only way you do that is really to eliminate that is more trials. The only way to eliminate random error is more trials because the idea is that if you do enough trials, the random error will eventually average out. Like if you're too high 7 times, you're too low 7 times, it'll average out. And the more trials you do, the more likely it'll average out. But there's not other solutions for random error. If it's a random error, the only solution is more trials. Because there's no way you can prevent random errors. You can maybe minimize it by doing more trials, but there's not a way to prevent it. Okay. So you got it, Zach? Yeah. I mean, that's okay. Systematic error. The number one systematic error of every calorimetry is heat loss to the surroundings. That's the number one error that you have for all these. And if heat is lost to the surroundings, that means less heat is going into the water. And if less heat is going to the water, then your delta H is too small. Maybe it's less negative or less positive than it should be. But this is always a thing. Okay. And remember, systematic errors affect accuracy. So more trials doesn't help. Because if you're having the same error too low every single time, then no matter how many trials you do, you won't get any more accurate. So systematic errors are not helped by more trials. They are a procedural thing that you have to improve. Okay. So heat loss surroundings can be minimized by using a lid, better insulation, factoring in beaker heat. So if you knew the specific heat of the beaker or the heat capacity of the beaker, you could add that temperature, that heat exchange into there as well. Like we said, stirring is also another way because the faster the reaction happens, the less time you have for heat loss to surroundings. Beaker heat, sorry. My handwriting is. So like factoring in, like for combustion, when factoring in how much heat is being absorbed by the beaker would also make your values better. You know, um, let's see. Reaction doesn't go to completion. So therefore your delta H is smaller because it's not producing as much heat as it should be because it doesn't completely react. Again, I think that's more with stirring and things like that as well, trying to make sure it completely reacts. What if you see solid carbon forming on the beaker when you're burning a fuel? Not enough oxygen, which means incomplete combustion, exactly. And incomplete combustion produces less energy than complete combustion. Okay, so they might say a student was conducting a calorimetry with an alcohol burner and a beaker, and he noticed that there was a black residue forming on the beaker. State and explain the effect of this observation. So you'd say, well, he's producing carbon solid. That's what the black soot is, which means the alcohol is undergoing incomplete combustion, which is, again, less heat. So your delta H would be smaller. It is, yes. I don't think they would like kind of do double errors and stuff like that. They would just focus on one error and how you'd improve that, not thinking about how it might affect other situations as well. Okay. Now, I'm also going to mention in here a couple of the things about the measurements and calculations because this might be a case where they demonstrate a calculation and state what's wrong with the calculation, like what mistake did the student make. And so remember, in this experiment, you're doing change in temperature. Okay. So let's say you have 14.2 plus or minus 0.5 degrees Celsius minus 18.6 plus or minus 0.5 degrees Celsius. Your change in temperature is negative 4.4 plus or minus 1.0 degrees Celsius, because we have to add the uncertainties. And they might ask you to calculate this with the right value. Okay. And remember, for like Q equals MC delta T, your mass might be, I don't know, 100.0 grams plus or minus 0.1 grams times 4.18 joules per grams degrees Celsius. And then negative 4.4 plus or minus 1.0 degrees Celsius. But if you're calculating the uncertainty there, because you're multiplying values or dividing values, you have to do the percent uncertainty. So 0.1 over 100 plus 1.0 over 4.4 times 100. And that gets you your percent uncertainty for this. So make sure you remember how to process uncertainties, whether you're adding and subtracting or multiplying and dividing. Yes, you could. You could just turn it into a decimal and then multiply by the value, correct? Yes, correct. Questions on that? I think let's try to get a third experiment in there because we still have some time. Y'all are expected to be here till 11, right? Let's get a third experiment in here. That means we'll have to worry about less the next time. Let's take a 3-minute break and then we'll get back into this. We'll finish it. Or 5-minute break. 5-minute break. Okay, so this is the third experiment called gas collection over water. Okay. Okay. Generally, the purpose of this is determine the molar mass of a gas. Okay. So you could also use this as rate law, rate measurement as well, because you can collect the gas production. But I'm going to kind of focus on the gas law part of this. Okay. So what you're going to have here is usually something like this. Let's see, how do I do this? Like, let's say, see, I have this a little bit differently over here, but I'm going to do it a little bit differently than I have in here. So let's say you have like, I don't know, like, yes. No, it's just one. Yeah. So we don't need to subdivide it. So for example, here, we might know that it forms a diatomic gas, but we would need to collect the gas over water to kind of get some information about it to figure out what it is. Okay. So pieces of equipment that are specific to this experiment. Eudiometer. Okay, so eudiometer is essentially an upside down graduated cylinder, but it's a little bit more precise than that. That's why it is kind of very skinny in this case. So it starts with 0 up here and goes like 50 down here or 100, depending on what eudiometer you have. Okay. Centimeters cubed, yeah, usually in centimeters cubed. Okay. Now, there's a lot of different ways that you can kind of set this up. Sometimes you'll have like a rubber tube or a glass tubing that connects here to funnel up the gas here. And so usually what happens is you have a beaker, a flask here. Where the reaction is taking place. And we collect this gas in a beaker that's full of water. You know, let me color this in like this so you can still see stuff. And we fill the eudiometer with water as well, and then the bubbles displace that water and push it out of that container. Okay, I do understand that my glass tubing is going right through my beaker. That's not like exactly correct, but you get the idea. Huh? Like it should be obviously over the beaker, like underneath there. Like y'all remember in our class, like we did it in like a trough. Yeah, we did this experiment. So you had like a trough, and the flask was hooked up to the hose, and then the eudiometer was like collecting gas over that as well.
And it's the beaker's filled with water, correct?
Yes, the beaker's filled with water. Okay. Wait, what? Okay. How are our flasks looking, Sol? Okay, cool. Okay. So, couple of tips, okay? Eudiometer should have no air bubbles because air bubbles will affect the volume that you're recording in the eudiometer. Okay. 2, you want the temperature of the water to be equal to the temperature of the room because you want some consistency there when you're measuring the temperature of the system here. Okay. And 3, when you record the total volume, make the water levels match. So if you're really being precise about this, when you have all your gas collected, you will move the eudiometer up and down in the beaker until the levels are matching. And I'll explain to you why that's the case. Okay. The reason why you need to do that is you want the water levels to be the same inside and out. The reason why that is because you want the pressure of the atmosphere equal to the pressure of the gas plus the pressure of the water vapor in there. So you want to be able to assume that the pressure inside the udiometer is equivalent to the pressure of the outside. So you need to have those water levels to be the same, because that allows us to make an assumption. That these two values are equivalent, that the pressure of the atmosphere is equal to the pressure of the gas plus the pressure of the water vapor. Because anytime you have gas collection over water, even though there's empty space above the water, there's water vapor there and the gas you're collecting there as well. Y'all may have done this with cigarette lighters. I think y'all did in 11th grade, where you like bubble the cigarette, like the butane gas, into the udiometer to measure the molar mass of butane. Okay. Same idea. Okay. We did a similar lab, yeah, in December when we were doing like different techniques. Yes. Huh? No, we did an actual reaction. Yeah, we did vinegar and baking soda, just so y'all could get the technique down. Okay. So data collection, data that you need to have. Okay, one, the mass of the metal that's reacting. Two, the temperature of the water. Three, the volume of gas collected. And four, the atmospheric pressure, the pressure of the atmosphere. And like I said, they might have you subtract the water vapor pressure from this to get a more accurate gas pressure. They might not. But if you're actually doing it scientifically correct, you want to subtract water vapor pressure. Yes, Christoph. No, you should always take that into account. So like when we do the experiment, like when I do the experiment, I look up the local barometric pressure to use that as my value. So it will change. Like the pressure will change depending on altitude, which will affect your values. So yes, but that's why you always try to look it up right before you do the experiment. Yeah. So yes, this experiment would still work in Colorado. Your volume would just be bigger because you have less pressure pushing against it. But then that would all work itself out because they're inversely proportional. Okay. Questions? Okay. Now, for analysis, remember, you want the molar mass of the gas, which is equal to the mass of the gas divided by the moles of the gas that you produced. So we need these two values to be able to solve this following answer. So we need PV equals nRT to figure out the moles of gas we produced. So remember, pressure is in kilopascals, volume is in decimeters cubed, N is moles, R is 8.31 joules per mole per Kelvin, or yeah, and then temperature is in Kelvin. And that will help us solve for the moles of gas. Okay. How could we calculate the mass of gas being produced in this reaction? Because we know how much metal we reacted, right? So what we could do is take the mass of metal and convert it to the mass of gas using stoichiometry. And those two values would allow us to be able to calculate the molar mass of the gas here. Bless you. Questions about how I got those two values? Yes, Christoph. Well, it will be the pressure of the gas. So if the experiment doesn't tell you what the vapor pressure is, then that is the same. Yes. But if they tell you the vapor pressure, you need to subtract that from the atmospheric pressure to get the gas pressure. Yeah. So it's, yeah. No, no, no. A finds the moles of gas. B finds the mass of gas because you can't know the moles of gas because you're not at standard temperature and pressure. So you can't use 22.7. So correct. Yeah. Because you can do a mole to mole ratio and oh wait, hold on a second. Maybe I'm saying this wrong then. Yeah. Wait. Okay. Hold on a second. Then what was I trying to say there then? Because like, then how would you find the mass of the gas then? Because I know how to do it. Hmm. Yeah. Now that I think about it, because you could get the moles of the gas, but you couldn't figure out the actual mass of the gas. Because the only way that I usually think about this is like with the butane lighter. Like when you do the butane lighter, you're measuring the mass of the butane lighter before and after, and that tells you your mass. But I'm trying to figure out now, like, then what would they want to? Oh, you know what? I would probably tell you that in the problem they just give you the mass of gas. Like I would say that if they were doing this problem, they'd most likely just give you the mass of the gas collected. Yeah, part B would have to be given here. Correct. Right, you could do that. Correct. Okay. Now, we'll focus on systematic error on this one as well. Okay. One, if you have bubbles in the UDometer, how does that affect your data? If you have bubbles in the UDometer, how does that affect your data? Yes, Christoph. Right. So you have a higher volume than you actually are supposed to have. And if you have a higher volume, what ends up happening to your calculation? Yeah, but how so? Which one is it? You're trying to solve for moles, right? You have a higher number of moles because it's on the opposite side. So yeah, because then the value on the left would be too high. Yeah, you're solving for moles. So then you'd have higher moles, which would mean lower molar mass. You see it? Oh, okay, yes. You have a lower molar mass overall. Okay, two. Reading meniscus. Okay. I know this is a technique that you're supposed to know, but I do want you to understand like how this affects it. If you're not at eye level for the meniscus, that affects what your value is. If you're too high, then you read a value that's too low. And if you're too low, like you're not at eye level, actually, it's still too low. Oh, no, you'll see this. You'll see this value. Sorry. You'll see that value. So it's too high. So understand like reading the meniscus, and it matters here because you're not doing the difference. In titration, it doesn't actually matter because you're finding the difference, and as long as you measure it the same way, it won't matter. But in eudiometry, you're only measuring it once, so it does actually affect your data. Okay. Other kind of miscellaneous things, depending on the experiment. If you're doing the butane lighter, then you might still have water in the lighter, which makes the mass of the butane lighter appear higher afterwards, which makes the mass of butane less. And two, if CO2 is your gas, it is slightly soluble in water. Okay. So, what do you think the problem is if the CO2 dissolves in the water? What will happen to the volume of gas you're collecting? Lower. It'll be too low. Because if some of the CO2 doesn't displace the water and dissolves in the water, then you'll have a lower volume, which means a higher molar mass. Okay.